with or without replacement? That is the question. Often in our probability or statistics course, we are presented with a sequence of events followed by the words with replacement, or they are followed by the words without replacement. Our motivation today is to simplify the instructions with and without and show in a few cases the probabilistic differences between the two. As we often do here at AI, we will show a mid-level case, an exaggerated small case, and then an exaggerated large case. This will allow us to really hone in on an understanding and give us a better idea of which experiments would use the with terminology and which would use the without terminology. So let's begin by rolling some dice. No, wait. Scratch one of those die. You're only going to roll one die, where the pips or dots on each side indicate the number. You've all played games with dice, so you know that one die will show a count between 1 and 6, inclusively. Now, to go along with the die, we have a hat with 1 red chip and 5 blue chips for 6 chips total. So we're going to organize the chips to relate to the die. Let's label one of the blue chips as 1 to relate to the 1 on the die. The next blue chip we will label 2 to relate to the 2 on the die. The red chip we will label 3 to relate to the 3 on the die. And the rest of the blue chips will be labeled 4, 5, and 6. Now, if I roll the die, there is a 1 in 6 chance I roll any one of the 6 numbers on the first roll. Suppose I roll a 5 on the first roll. What is the probability of rolling a 3 on the second roll? Well, since the number 5 has not been eliminated from the die and still could show up on the second roll, we then define this as a with replacement problem, because 5 is still a possibility. Since 5 was not taken out after being rolled, then rolling a 3 on the second roll is still 1 out of 6. Similarly, the probabilities of the third roll, the fourth roll, and so forth will always be the same. Rolling a 3 on any roll will be 1 out of 6. Likewise, rolling a 1 on any roll will be 1 out of 6, and the same probabilities go for rolling a 2, 4, 5, or 6. Now let's look at a without replacement example in the form of the hat with chips. Remember, we have a red chip labeled 3 and the other 5 numbers were assigned to the blue chips. Now if we choose a chip from the hat and it happens to be a blue chip 5 and we don't put it back into the hat, that's without replacement. What is the probability I pick a red chip 3 on the second choice in this without replacement problem? Well, on the first choice, we had a 1 out of 6 chance of getting that red chip. Since we didn't get the red chip on the first choice, it is still in the hat, but there is 1 less blue chip. This increases our chance to a significant degree of getting the red chip on the next choice. On the second choice, the potentials are 4 blue chips and 1 red chip, or a 1 out of 5 chance. Again, our probabilities have improved because we have decreased the number of blue chips that could be chosen. If we choose a blue on the first choice, blue on the second choice, of course, without replacement, the probability of choosing a red chip on the third choice has improved even more, because now there are only 3 blue chips and 1 red chip. So our chance of choosing red is 1 out of 4. So real quickly, let's look at an exaggerated example. Heads, tails on a coin versus 1 red chip with heads written on it versus 1 blue chip with tails written on it. Now, if you flip a coin, first flip, and get tails, what is the probability of getting heads on the second flip? Correct, 50%. The probability of flipping a heads on any flip is 50%. That's because tails always remains a possibility. It's considered a with replacement problem. Now, we move back over to the hat. But like we said, there's only 1 red chip with a heads written on it and 1 blue chip with tails written on it. Now, if on the first grab from the hat relating to a flip, the blue chip labeled tails was chosen and we don't replace it, meaning we don't put it back in the hat, or without replacement we call it, then what is the probability of choosing the red chip with heads written on it on the second pick? And again, you are correct. The probability is 100%. Since there's only 1 chip left in the hat, and we know that the chip left in the hat is red. At some point, with or without replacement may not make much difference at all. For instance, in a large sample with 1,000,000 blue chips and 1 red chip, the difference of with and without probabilities on the second choice won't make much difference if the first choice was a blue chip. If we replace the blue chip before the second pick, there are still 1,000,000 blue chips. So the probability of choosing red on the second pick is 1 out of 1,000,001, which is 1 over 1,000,001. In the calculator, it looks like this. Now, without replacement, with 1 blue chip taken out, statistically does not change the story. It's 1 out of 1,000,000, which in the calculator looks like this. Both of these accounts represent a 0% chance of picking the red. So what does that tell us? Well, without replacement can dramatically change the probability in small sets, must be considered in medium-sized sets, and really has no impact in very large sets. Essentially, buying a second lottery ticket without replacing the losing first ticket does not improve your odds. The chances of winning the super jackpot is still an incredibly low 0%.
Hey, Alien Institute crew! Don't forget to strike the like, subscribe, comment, and share. Also continue learning by watching more AI videos.